we were talking about the core generator system, which is the design automation tool that Xilinx provides that allows you to create customized cores for your design. And we said that what the tool will output is 3 files, a netlist file, an instantiation template file, VHO for VHDL and VEL for Verilog. And it's just an ASCII file that tells you the syntax for instantiating the core that you created. And then we have this wrapper file that's used for simulation. It's a .v file, and you do not synthesize it. It's only used to support simulation. Okay. So I want to look at FPGA implementation. And this is a simplified diagram. So I have my synthesizer, and it has the 3 inputs of the library, the hardware design language description, Verilog or VHDL, and design constraints. And out of the synthesizer, you get a net list. The net list then goes into implementation tools. And I have, for example, PAR. Which is place and route. And you'll see that abbreviated either one of those ways, so you should be familiar with both ways. So PAR is place and route. I prefer PAR, place and route. And then out of the place and route, you get that binary bit stream that you're going to use to actually download into the FPGA program. So that Xilinx Vivaldo that you've been using is more than just a synthesizer. It's a design suite. And it has both the synthesizer and the implementation design automation tools all encompassed into one. So when you apply your library, your constraint, and your hardware description language into Vivaldo, Vivaldo actually does all of the synthesis and implementation for you and generates the binary bit stream, which is then downloaded through JTAG, which is something we'll take a look at a little bit later. So your synthesizer is only generating a net list of the design. And that gives rise to an issue related to FPGA vendor IP that they provide. And it goes back to that issue of the 3 files that are generated. If you look at that intuitively, that net list generated by the synthesizer is generated from the HDL. But the core generator doesn't give you a .v file that you can synthesize. The .v file is for simulation only. So, the IP generation tools create IP, which is commonly referred to as a hard macro. Some people say it's hard because it's hard to do, but at any rate, that's the name used. And I listed up there 4 different FPGA vendors. The IP generation tool they use, Xilinx uses CoreGen. And the file format that they output could be EDIF, ADL, and so forth. This .ngc file is the one that I explained before from CoreGen. Well, you have a little bit of a problem. Those file formats that give you the net list are understood by the place and route tools, not the synthesizer. Synthesizer only understands Verilog or VHDL, doesn't understand netlist files. So how does your IP core get into that design? Yeah.
So I guess I'm a little confused. So those file types that are listed up there are the outputs of core generation, and those are basically also the outputs of the synthesizer. Those file types are the synthesizer outputs. Is that
No.
okay?
They're generating what a synthesizer would have generated,
Oh,
but it's a netlist file.
right.
Okay? Synthesizer doesn't take netlist files as input. Takes Verilog or VHDL,
But you
along with a library and user constraints.
But then you could just bypass the synthesizer altogether.
Yeah, we'll get to that.
Okay.
That's the question down there at the bottom. Well, synthesizers don't understand the netlist files that the IP generation tools generated. How does that core that you created get into the design? Everybody understand the problem? Okay. So to illustrate this concept, I want to look at an example. I have a module there called FIFO top. I've got some declarations. And you'll see in the always block there that I've implemented a basic counter. If the reset is a logic 0, the count is forced to 0, otherwise the counter increments. And let's see, this is a 16-bit count. Okay. I've also instantiated in here a module myFIFO, and I've got connection by name. And I'm assuming that myFIFO was generated by an IP generation tool. So that IP generation tool will give me a behavioral file, .v file, which I can use to simulate to verify that this FIFO top module functions correctly. But the problem is, how does the net list from this get into the net list that is going to be required for place and route? How does the synthesizer incorporate that design, that core, into its netlist output? Well, the answer is black box synthesis. Okay, so these black boxes are placeholders. In the synthesizer netlist output. Effectively, what I'm going to do is, in my Verilog code, that HDL is going to be an input to the synthesizer, I am going to define a black box. And I'll show you how to do that. A black box for that core that I generated through an IP generation tool. So it's just gonna be a placeholder. Then when the net list generated goes to the place and route tool, that's where the .ngc file gets input. Because place and route says, okay, you got a placeholder in here, and there's supposed to be net list information on that core. Where is it? Well, you got that .ngc file. That's where it gets input. So the .ngc file actually gets input to the place and route tool, not to the synthesizer. So effectively what you're doing is, here's your synthesizer. And the output is your net list. If I can spell. And right here is a placeholder for the core net list. All you've done is identify, okay, there's a space in here and that's gotta be inserted. Now place and route can have all the information it needs to actually do the implementation. Okay, so. Black boxes are defined only by their I/O. And no functionality. Okay. Now, I'm also going to need a synthesis attribute. And the purpose of that synthesis attribute is to tell the synthesizer, hey, I've got a black box. I'll tell the place and route what the net list is. I will tell you the signals that would go into this module and come out of this module. But just leave a space in the net list for that to be plugged in. So you're gonna need this synthesis attribute as well. Now some notes. Since there is only port information and no functionality, the synthesizer doesn't implement the module. It doesn't know what functionality the module is going to do. How can it actually implement that particular module? This has implications for timing and area optimization. If the synthesizer doesn't know what the functionality is, how is it going to implement? And it can't implement the module. It can't apply any optimization for area, for timing, or whatever. That's why it is so contingent upon the core manufacturers to work with the Xilinx, or whatever the FPGA vendor is, to make sure that their cores that they are going to sell you or provide to you have been optimized for that particular family of FPGAs in terms of timing and area. Because you can't rely on the synthesizer to do that. The synthesizer doesn't have the information necessary to do that. So presumably, the net list that is being generated by the IP generation tool has all of that built into it because they've been working with the FPGA vendors. There is one thing, however. Since the synthesizer knows the I/O, the design hierarchy is preserved. Okay? Because you partitioned your design and everything, the module is identified, it is going to be part of your design hierarchy, so you still are able to preserve that. So here's how I would create a black box for that my FIFO that I use an IP generation tool to create. I have a module, end module. You'll notice all I have done is declare the input and output. And then I include this synthesis attribute, synthesis SYN underbar black underbar box. I just define the ports. There's no functionality listed. It's empty as far as functionality. I just tell you what the ports are and I put in that synthesis attribute. Now there's some notes associated with this. Again, you're only defining the ports, no functionality. This synthesis attribute right here informs the synthesizer that this is a black box. If you do not create a black box module, this will generate a synthesizer warning. If I tried to synthesize that code that you previously saw and I hadn't done this black box module, I'd get a synthesizer warning. Some synthesizers may actually generate an error. But the warning will usually say something to the effect of, well, I didn't have any information, so I'm just presuming it's a black box, and that's the way I'm going to implement it. Well, those warnings can be very irritating. That synthesis attribute purges all those warnings. You won't get them because you've actually defined a black box. Okay. Now, when you get to the place and route, the net list that it got from the synthesizer is going to say, here was a black box module, and the place and route is going to say, okay, do I have net list information to do that? If it doesn't, then place and route is obviously going to fail. And place and route will issue a error and says, you got a black box module and I don't have a clue as to what to do about it because you didn't provide that .ngc file, that edif file, or whatever that the core generator produced. Okay? So, go back to this. Those are the three files the IP generator is going to produce for me. I get the instantiation template file so I can instantiate that core into my design. I'm gonna get a wrapper file so I can do the simulation. And in my code, I will have a black box module created. And that netlist file then would be input to the place and route. And everything's complete. And that's how you put your core that you use from an IP generation tool into your design. You'll instantiate it in a module you write. You use the wrapper file to simulate your entire design, and then you take the NGC file and provide it the place and route. And by creating that black box, you've left a place for it to be inserted into the netlist that the place and route gets from the synthesizer. So it's important that you know how to do the black box modules. Okay, they're real simple, but you have to use those if you're going to incorporate core from an IP generation tool into your design. Does that make sense? Okay. Now let's talk about get the right thing in our notes. I think we're going to talk now about configuration. I think. We are. Incidentally, I'll make a comment about the wrapper files. I haven't looked at one, so I can't tell you exactly how they've implemented for a particular core. Obviously, it's going to be dependent on the core that you're using. But it says that it's not synthesizable. And here's one way, at least on a simple core, that it could be implemented. There was a chapter in the Palatnikar book that we did not go through that talked about user-defined primitives. User-defined primitives are valid Verilog code. There's a specific syntax and semantics associated with it, but they're not synthesizable. And one of the reasons they're not synthesizable is it gives you, for a design, the most broadly based, least information available description of the behavior of a circuit. Now let's take a combinational logic circuit. What is the way that you could describe how that combinational circuit is supposed to behave and give me the least amount of information as to how to actually build it? What form would that behavioral description be? Think in terms of not Verilog, but how would you describe the circuit? I could describe it by giving you a schematic, right? But that tells you what gates to use and how to connect it. What's another way I could do it for that combination logic circuit? If I don't give you a schematic, how could I tell you what the circuit's supposed to do? How is it supposed to behave?
Using Verilog too.
Forget hardware description languages.
You could
Boolean equations, I can give you the Boolean equations. That would at least give you a clue as to what types of gates to use, because you know that there were AND functions and OR functions, etc. What's another way I could do it?
Truth table.
The truth table. All the truth table tells you is, for these inputs, I want those outputs. There is no information on how to implement it. Well, guess what user-defined primitives are? It is a Verilog syntax that essentially constructs a truth table. Well, if you give that information to a synthesizer, the synthesizer really has to do one bang-up job to figure out how to implement it, because you've given it no clues whatsoever. You've just said, for these inputs, give me these outputs. And so I think for one reason why no synthesizer supports user-defined primitives is because it's just too difficult to deal with for other than a very simplistic type of circuit. That's the reason why we didn't cover user-defined primitives in the Faltnicar book, because I wanted to emphasize teaching you Verilog from the standpoint of synthesizable code. But the wrapper file could be, for a simple module, a user-defined primitive, because user-defined primitives are simulatable, but they're not synthesizable. Okay. So if I ever get a cursor here, if I never get the cursor to move. How the heck did I get that? So what we're going to cover now is how do I actually program those FPGAs? My place and route tool has given me my bit stream. Now how do I get that information into the FPGA? Oh, they have the spring, they have the fall quarter up now. Didn't know that.
Hello, and welcome to this recorded e-learning on basic FPGA configuration, part 1. My name is Frank Nelson. I'll be your instructor for this module. This module is intended to introduce you to FPGA configuration so that you can choose the appropriate configuration scheme that best supports your application. Please note that we recommend you listen to the basic FPGA configuration 2 recorded e-learning.
And we're not going to go all the way through this one either. But,
If you are an experienced ASIC designer or new to FPGA design, this module will help you reduce your learning curve and get productive faster with your new FPGA design. This module will help you understand the configuration process. The configuration principles and configuration modes I'm about to describe apply to virtually all Xilinx devices, except where noted in the recording. This particularly applies to some of these slightly older architectures. After completing this module, you'll be able to
Can you hear
describe
that, or do I need to
FPGA
turn it up?
configuration pins. This is essential because the configuration process is relatively automatic after the configuration scheme has been selected, and this is done by pulling the configuration mode pins high or low. You'll also understand the differences between
I'll show you some examples of the mode pins a little bit later on.
From this information, you'll be able to choose an appropriate FPGA configuration scheme. Before choosing a configuration scheme, however, you must know some of the basics and understand the advantages or disadvantages of each scheme. This module is intended to highlight why customers choose one configuration scheme over another. The basic FPGA configuration 2 module will introduce you to daisy chains and prototyping hardware that is available to you. It will also answer the most frequently asked questions about the FPGA configuration process. What is configuration? Well, configuration is the process of loading configuration data into your FPGA. This is necessary because the FPGAs are SRAM-based. SRAM cells are not static and lose their programming when they lose power. Unlike flash cells, which are static and never lose their programming unless they complete an erase cycle, FPGAs lose their programming each time they are powered down. This brings to mind the question, why are FPGAs made with SRAM logic and not flash if reprogramming is going to take extra effort and cost? Well, the answer to that is that SRAM cells are much smaller than flash cells, and FPGAs offer much larger densities.
Okay, so that's an important point. why is that there?
It's just suggesting other videos since you paused that one.
Yeah, no doubt. The FPGAs are SRAM based. They could be, in principle, made non-volatile, so you only have to program them once. But those memory cells are larger than static RAM cells, and the objective here is to get as much stuff into the package as possible, so they're SRAM based. There have been, in the past, some FPGA architectures that actually had the SRAM, but underneath that, they incorporated into the chip non-volatile RAM. You actually programmed the non-volatile RAM, and when you powered up the FPGA, it would dump from the non-volatile RAM into the SRAM, and away you go. That took up too much room, so that died out. So the issue here that we're dealing with is if I have something like a smartphone and I've got an FPGA in it, it's SRAM based. I'm not going to plug my smartphone into a computer every time I power it up to download the information. So somehow on the printed circuit board, I've got to provide a means of configuring, of programming the FPGA. And so he's going to discuss in here 4 different ways that that can be done, where you could have a standalone system, a medical instrument, a smartphone, or whatever, SRAM-based FPGA, you power it up, and it automatically gets configured.
CPLDs. So since we're using a large FPGA, then we need to plan on having a memory component somewhere that can store the FPGA's bit stream. In general, each of the configuration modes supports a variety of configuration methodologies. Keep in mind that FPGAs are designed to offer a wide range of configuration solutions, in which some are simpler and need less debugging, and some are less expensive and give you a choice of memory components, and some offer a great deal of flexibility to suit a wide range of applications. In this example, the configuration data source could be at its simplest a flash memory component, or the bitstream could be stored on a network or downloaded from a laptop computer. The control logic shown in this diagram would have to be customized by the user. If the designer did not want to build this extra control logic, there are additional master configuration modes that use dedicated control logic inside of the FPGA to program the FPGA with a bitstream stored on a variety of memory components. The supported memory devices include a Xilinx PROM, a byte-wide peripheral interface, or BPI PROM, or a serial peripheral interface, or SPI PROM.
Which is the one I'm going to talk about
Depending on
in
the
detail.
configuration mode you choose, there are 2 types of data paths, serial and multi-bit. Serial data paths are used to minimize the number of device pins required. Multi-bit data paths offered include by 8, by 16, and by 32 bit widths. These are used for higher performance or enable access to industry standard interfaces. These multi-bit solutions are ideal for connection to external data sources like processors or parallel flash memories. In the end, every configuration scheme has advantages over another. Some configuration modes are designed for debugging, while others lend themselves to maximizing the system's available memory resources, and still others might give designers a choice of vendors. Choosing a configuration technique just requires the user to understand what their system is going to have and to anticipate what they're going to need their system to do. In some instances, customers build their configuration scheme to include multiple configuration modes, so they can test and debug their system through one configuration scheme, and then configure their FPGA through still another scheme after the product has been released. Like processors and processor peripherals, Xilinx FPGAs can be reprogrammed in system, on demand, and an unlimited number of times. In fact, some customers take advantage of the reconfigurable nature of FPGAs to the extent that they have multiple bit streams loaded onto their system. This feature is referred to as multi-boot. Multi-boot can save the cost of purchasing another FPGA or even a larger ASIC.
How many people have thought about that? If I have some sort of non-volatile memory on my printed circuit board that has configuration information, I could have, there's no reason why I just have one configuration bit stream. I could have multiple ones, which means that sometimes I have the FPGA do some functions, and in another case, I may have it do completely different tasks. Yeah.
About how long does it take, like, if you wanted it to go from one configuration to another, about how long would that take to like reprogram it?
Well, you could do it, for example, this is just a simple example. Let's suppose that I have two flash memory chips, each one having a different configuration. I could have a jumper on the board. One of those where you have two pins and you have one of the slide-on
Yeah.
connectors. If I pull the thing off, it'll download from one of the flash memories. If I put it on, it'll take the other flash memory configuration. So just by moving or installing a jumper, I can completely change what the FPGA does.
But you can like, so I guess I heard some people like when there's a lot of design, I guess they're sort of speculating about what they're gonna do with FPGAs like on like CL chips and have it like reconfigurable, just sort of like as it's in use, just like, oh, I need
Oh,
this
without
now.
physically removing the
physically
jumper.
moving, just like, oh, I need this, and oh no, I need to be doing some other task.
Yeah, you could do that. For example, if I had a, separate to the FPGA, a microprocessor of some sort.
Yeah, I'm just wondering, like, in the world of like high-speed microprocessors, how
Yeah, the microprocessor
slow
then
is that good?
could set or clear a bit, that's a select line for a multiplexer. So the microprocessor, through that multiplexer, could say, load from memory chip A or memory chip B. Because remember that when we talked about the Vertex 5, there was only the FXT versions that had an on-chip microprocessor. If you were using another one of the Vertex 5s that did not, and you had an external microprocessor on the board, that could control which memory loads the configuration. So you could adapt the behavior.
I mean, does it take like a second or half a second to process a program in FPGA like that? Or is it?
Well, he's gonna get into that. That's one of the modes where the well, if you have a microprocessor program the FPGA, that's different than what I just described.
Okay.
The FPGA would actually be communicating directly with the microprocessor. The microprocessor would be reading the configuration information out of memory and then writing it to the FPGA. That's different than the microprocessor selecting one of two multiplexer inputs.
Okay.
And the inputs to the multiplexer would be separate memory chips. That's a different configuration scheme.
So as I just described, configuration must occur on power up, but can also occur on demand by toggling the FPGA's program B pin. So as I just described, configuration must occur on power up, but can also occur on demand by toggling the FPGA's programming pin. Additionally, configuration can be triggered with commands over the select map or JTAG ports without having to toggle the program pin. FPGAs need to be configured because their SRAM cells are volatile. The user will have to plan on storing the configuration data in a PROM or some other external data source. To build your system, you'll have to understand the basic configuration process and how to set up various configuration modes and daisy chains. But before you can get to that point, you'll need to understand the advantages and disadvantages of each configuration scheme so you can choose the appropriate mode for your system.
Let me explain that term daisy chain. I've got on the board a non-volatile memory that's got configuration information. I'd have configuration information for 3 or 4 FPGAs that are on the board, all contained in that one memory. What you have to do is effectively create a shift register so that you shift the data in through all of the FPGAs. They're kind of daisy chained together to form a big shift register where instead of flip-flops, you've got FPGAs. And the one memory chip serially configures all of the chips simultaneously. that would be a daisy chain. I'm primarily gonna focus on a system where you only have one FPGA that you have to worry about configuring. Here's your configuration.
Well, there are lots of configuration possibilities to consider. The first we're going to consider is configuring via a Xilinx download cable. These cables allow the user to reconfigure their FPGA with only a download cable and their computer. The configuration modes described are used primarily for prototyping and debugging and design. These cables are low cost and are typically used to configure the FPGA in a JTAG configuration mode. We will discuss the additional hardware available in the basic FPGA Configuration 2 module. Configuration can also occur with the use of a microprocessor or microcontroller.
We're gonna go through that, but let me summarize the 4 methods for you. In the upper left, you have the Xilinx cable. That's where you have your printed circuit board with the FPGA plugged into a PC. And you're gonna download from the PC to the FPGA. That's the scheme that's used over there in the lab when you did your synthesis. This one down here is where I have the microprocessor that's on the printed circuit board, actually responsible for doing the programming of the FPGA. The other 2 methods, the one in the upper right, Xilinx Proms, is Xilinx specific, but both of those techniques have on the printed circuit board some sort of non-volatile memory that contains the configuration data. And the FPGA communicates with the memory chip to get its configuration data when power is applied.
So,
Yeah.
I'm sorry, I'm a little confused. When we started this whole thing, you had said that they didn't include non-volatile memory on there to reprogram it, but it seems like all of it is including non-volatile memory.
No, they didn't put non-volatile memory inside the FPGA chip.
Oh, so it's somewhere else on the board.
Correct.
Okay, okay. That's right.
And in fact, I'm going to show you an example of for the SPI, serial peripheral interface, which is the main one I want to focus on in this class. That memory chip is only 8 pins. It's an 8-pin flash, surface mount technology, so it's in like a small outline IC package. It will fit on the tip of my finger. It's that small, but it can contain megabits of configuration information. We'll take a look at one of those. But the non-volatile memory is external because, as he said before, the FPGA SRAM cells are smaller than if you made a flash. And so I can put more stuff in the package if I go with SRAM. So the non-volatile memory will be on the printed circuit board, but external to the FPGA.
These configuration schemes involve some other external control logic being used to control the configuration process. In these configuration modes, the FPGA is a slave to whatever control logic is managing the configuration. These configuration schemes require extra components and thus have added cost associated with them. Most users consider this configuration scheme if they already have the external control logic available as part of their system. Configuration also can be completed using the Xilinx Platform Flash PROM. These configuration schemes usually use the FPGA's built-in configuration logic to control the FPGA's configuration process. With these components, the FPGA usually configures itself. These configuration schemes require the user to buy a PROM, which has some additional cost, but these schemes are usually the easiest to debug since the control logic is already fixed as part of the FPGA. We will talk about the Xilinx Platform Flash products in the basic FPGA Configuration 2 module. Some new configuration options have just become available to Xilinx users. The Serial Peripheral Interface, or SPI, and the Byte-Wide Peripheral Interface, or BPI, configuration schemes allow users to purchase off-the-shelf commodity flash components. The flash memory can then be used to store the configuration bit stream and for the user's application memory if the user is building an embedded system that would include some software. The configuration mode pins define to the FPGA what configuration scheme is about to be used to program the FPGA. This is important because the FPGA can handle several different schemes, and since each scheme behaves very differently from each other, the FPGA needs to know clearly and precisely what is going to happen next. If a user wanted to build a configuration scheme that included multiple configuration techniques, the first thing the designer would have to do is build the logic to drive the mode pins. There are 3 dedicated mode pins on the FPGA, and their simple binary combination defines the configuration scheme. The configuration pins each have their own purpose. Some are active switches, that is, inputs to the FPGA, while others are status indicators or outputs. Understanding their roles is the first step if the user is going to debug their own configuration problem. The configuration data stream is a little more complex, but understanding it is important if you're going to debug your own configuration problem. Note that configuration problems usually occur when the user is building a scheme that includes multiple configuration techniques. This is not especially challenging, but is a necessary byproduct of a designer, quote, doing it himself.
Okay, so the key thing here is, if you look at the FPGA data sheet, there will be 3 pins that are identified as mode pins. And depending on the binary pattern that you put on those pins will tell the FPGA which configuration mode to use. So when the FPGA is first powered up, it goes and looks at those 3 pins and says, I'm going to get my configuration information from X. And you'll have one pattern you put on if you're going to do it through serial flash memory, another one if you're going to use the JTAG interface or a microprocessor or what have you. So it's through those 3 mode pins that the FPGA will find out where is it supposed to go to get its configuration information.
Specific pins in the FPGA are used during configuration. Some pins act differently depending upon their configuration mode. For example, the clock, or C clock pin, is an output in some modes, while it is an input in other configuration modes. Some pins are only used in specific configuration modes as well. Now, this is a little challenging because each configuration scheme can differ so much. That's because each pin may or may not be used in different configuration techniques. This is why the datasheet and the user guide for each FPGA discusses each configuration scheme in detail. In fact, the user guide covers each configuration technique in more detail than we're going to provide here, so remember to review the section on your chosen configuration scheme. As I mentioned earlier, the mode pins define to the FPGA the mode selected. There are 3 mode pins, and they are inputs to the FPGA. The program pin is an input pin that is active low. It initiates the configuration process. So if you're going to reconfigure the device after it has already been programmed, then you will have to toggle this input pin to start reconfiguration all over again.
That's how you do on demand.
The clock pin is an input or an output pin depending on your configuration scheme. Note that if it is an output, the clock can run at up to 100 megahertz depending on the device you choose, but will default to a much slower rate. If you want to modify the configuration rate, you set the config rate attribute in the BitGen program. So check the configuration user guide if you want to modify this. The init pin has multiple functions. At the start of configuration, init goes low, signaling that the FPGA's memory is being cleared. After clearing, it is released to be pulled high by an external resistor. Later, when the FPGA is loading its bitstream, init can go low, indicating the bitstream has failed its CRC check, and the configuration is being aborted. The CRC check is a checksum that indicates whether the bitstream has been corrupted. The done pin indicates the completion of the configuration process. It's bidirectional, so the user can delay the startup sequence. After configuring the FPGA, the starting of the FPGA is often controlled by the user to control the releasing of the entire FPGA system to operate. On a side note, in case you don't know, BitGen is the bitstream generation utility included with the ISE software. It is used to create a bit stream from the implemented design and is used for configuring the device. Other important configuration pins are the data in pin, which is used to load in the serial configuration data. The data out pin is used to output the bit stream to the next device in case the user has built a daisy chain of multiple FPGAs into the system. A daisy chain, as we'll see later, is used to save PROMs or other memory components. It allows the user to store the bit streams of multiple FPGAs in one large memory component. To program multiple FPGAs in this way, the configuration scheme has to be configured to pass the data through each FPGA once it has been programmed. Now we'll talk a little bit more about this configuration later on. Some of the configuration pins are dual-purpose pins. After configuration is complete, they become normal user I/O pins. Users will sometimes prohibit the use of these I/O pins with the pin ahead utility. Check your device's datasheet or configuration user guide to determine which configuration pins are dual-purpose. Now, this slide will list all of the currently supported configuration schemes for all of our FPGAs. There are serial and parallel modes, first of all. Parallel modes are inherently faster, even though they may operate at the same speed, since they configure the device a byte at a time. The primary advantages and disadvantages include debugging time, debugging effort, cost, and speed of loading the bit stream. Now, first of all, configuring with JTAG is most frequently used when debugging a design. It is always recommended that customers include a JTAG configuration path so they can debug their design and system. No external control logic is necessary since the FPGA has a built-in JTAG chain and the external control logic is provided by the JTAG cable.
I'll be talking
Master serial
JTAG
is
later.
perhaps the easiest configuration technique to debug since the FPGA configures itself. This is the easiest to debug, but requires the user to purchase a serial PROM or a serial flash, such as the Xilinx platform flash. Slave serial mode uses external control logic that the user must design. This control logic has to feed a bit stream to the FPGA from whatever external data source the system has. Many customers store their data in a PROM or other memory resource in this case. SPI configuration mode is new. It requires the user to purchase a serial peripheral interface flash PROM. The benefit is that this configuration uses a price-competitive SPI PROM rather than another means to store the bit stream. It is also possible to use the SPI PROM to store software code in case the user is building an embedded application. This is a relatively simple configuration scheme to debug since the control logic is already a part of the FPGA. Now, there are several parallel modes which enable faster configuration than serial modes. Master select map uses FPGA configuration logic to be used and uses a parallel flash, such as the platform flash, to load the data a byte at a time. Slave select map allows the user to customize their configuration control logic and still load data a byte at a time. Note that slave select map also supports a by32 data line implementation when you target Vertex 5 or Vertex 6. BPI, or byte-wide peripheral interface mode, supports the use of an industry standard BPI flash component. It loads the data in parallel, so it is a faster configuration option than using a serial peripheral interface. BPI has the added advantage of allowing the user to store their software code with their configuration bit stream as well. Note that SPI and BPI are supported with Xilinx's newest FPGAs, including Spartan 3E, Spartan 6, Vertex 5, and Vertex 6. So here we have a diagram that describes the JTAG configuration mode. The TCK, TDI, TMS, and TDO pins are the only pins necessary for this configuration mode. All of the JTAG pins are standard and are dedicated on the FPGA. After they are used for configuration, they can be used as I/O pins or be prevented from being used for I/O. As configuration occurs, the bit stream for each device flows serially through each FPGA until the appropriate FPGA receives its programming information. Note that the control signals are each connected in parallel. JTAG access will override any other configuration mode. All the other modes require the mode pins to be set correctly for them and are mutually exclusive thereafter.
Okay, so, a couple of important things here. This is the scheme that's in the lab. JTAG only requires 4 signals. Test data in, test mode select, test data out, and test clock. 4 wires. That's why you plug it into the USB port. And I'm gonna take a look at one of those download cables and what it looks like a little bit later on. This shows a case where you have a daisy chain, where I've got multiple FPGAs that need to be programmed on the board. What you do is the test data in coming in from the computer can be routed to test data out to test data in on this one, through test data out to test data input on this one. So I would program this one first, then this one, then this one, all from the computer. The other important thing is he said that this JTAG overrides any other configuration mode. So if I picked a SPI configuration mode and I plug in JTAG, that allows me to override the SPI, and the computer will be providing the configuration information, not your flash memory. He made an important point here. Whenever you design a board that's got an FPGA on it, you need to provide a JTAG interface. It's only 4 lines, the 4 that you see there. So it's not gonna occupy any room or space or whatever. It's primarily used for debugging because your configuration information is on a PC. So I'm trying out different types of configurations to get my FPGA to behave the way I want it to. Debug mode. In practice though, if I've got a handheld instrument, some embedded application, I don't have that. I'm not using the JTAG interface because I'm not interfaced to a PC. Nevertheless, if something goes wrong and a field service engineer goes out to troubleshoot the printed circuit board, if you provided the JTAG interface, that field service engineer can have a laptop or whatever with test and debug software, and through the JTAG interface, configure the FPGA in some way so that diagnostics can be run. So you always need to provide a JTAG interface on any board that's got an FPGA on it. That's a given that you do that. It's not costing you anything, it's only 4 lines. There's no additional circuitry required, so it's only 4 traces on your printed circuit. Why don't we take a 10-minute break, and then we'll continue on. Like this.
Yeah.
I was debating on it too.
Yeah.
Get some sleep. Literally every class. I've never had a class with Aaron where he didn't sleep. Aaron, I've never had a class with you where you haven't fallen asleep. Every class. We've had like, I feel like 8 classes together or something. Like, you're always asleep. You need to get more sleep, man. People who don't accidentally get sucked into some random humble bundle game. Yeah, that was bad. That was very bad. I'm surprised I'm not feeling very tired.
At 5 hours, at like 5 or 6 hours a day. It's not bad. Baby, like,
Yeah, I got the coffee to try to.
you just need to get like
What happens if you, like,
a shot of adrenaline right to the heart.
Charlie, where'd you go to create your schedule for next year? Like, how did you figure out what classes were offered, which streams?
You can just.
Also, we can take. He'll get you into 581 over the summer too.
So you're not at post-bac, like registration phase?
No.
No.
Spring I'll be at all the fuckers, but we
So-
fall are like the last ones to register.
I'm hoping to like register for next week,
Wait, so
So you can find post-bac status, I mean, I'm gonna try.
we can also get into 581 over the summer if you're curious. I talked to Paul about it,
581.
which is something we probably need.
Which one is that?
He didn't even know. He's like, I'm like, what is 581? He's like, look it up. Something really basic.
Well, there were two things, and I knew that I could take one of them.
He said 581 is good. And he did have some strings like sign off on it. But, and how did you get the schedule? Like, how did you make your schedule for the coming years?
I have
I was gonna say, how do you know what classes are offered?
You can Google it, just like PSU classes offered when or something. There's a.
There's like a list. When I went to Duncan, they did like put down like the Fallner Springs, is like Springs. Huh? And then I'm just doing the basics. Money or fund out.
What is it?
Yeah, that's what
Yeah, because I can't financial aid for it. How come I think it's
the main like reason I can.
Yola, as they say,
I can't even,
a casual pre-grade.
I really don't want that to rent to.
So hopefully we can.
What is your neural, your genetic processing class about?
Oh, genetic algorithms?
Genetic algorithm.
It's supposed to be.
I know, I wasn't on campus. I thought we were going for this class today.
Trying to find a really good
Because
solution to it.
that's what we were
There
talking
are
about.
trillions of possible solutions.
Yeah, I have my class.
How do you search through the search space to find good
What
solutions?
were you saying?
Genetic algorithms.
I was saying after finals, what's a Johnny tradition of replacing our animals?
Uses
We should just go
to evolve.
after finals, after this final. If it's before the reset, if it's after the reset.
Emulated, don't we?
I was looking at some of the machine learning and neural net stuff. How people are trying to do it in hardware, and it sounds like that. Do you guys do it in hardware?
You can't implement genetic algorithms in hardware. In fact, it can be implemented. Some of the.
Let's play with circle cards after finals. They're all
Usually it's,
see, I don't know, it won't work though, like
Yeah,
all the
it seems like that
finals
seems to be
are
most of the neural network stuff is in software as well. It doesn't seem like it's really a good way to do it.
The thing with the neural networks is you consider the number of layers that you have to have, the number of nodes in each layer, that hardware wise it could get cost.
Yeah, they said it was
Like, right now,
the size.
Well, routing isn't too bad because it tends to be localized, depending on the neural network configuration. Your connections from one layer are open to the next layer. But there are things like the current neural network where you feed
Yeah, we
it.
were feedback,
And
yeah.
so now you've got more routing that you have to do.
Yeah, yeah, it's very interesting stuff.
This is a. AI engineering, how this is gonna be the panacea that's all
Yeah, I had it verbatim.
I've gotta get a copy of this.
I had no idea.
Gave a talk, and he had a long
And eventually it created it, so
talk
it's just like
showing
so
where we are on AI implementation. And what it was is a series of iPad. And they're trying to do simple things like, go down 2 steps.
Yeah.
I had no shame.
One of these things you see on ships, where you've got it's starting turning and falls over. So the notion that all of RoboCop movies.
Oh, yeah.
They had that one where
It's like, what am I doing?
machine guns got to a staircase, it's kind of doing this because it didn't know how to go down the stairs.
Yeah.
But AI is gonna solve all of that.
Yeah, I mean, it seems like everybody's always, it's every year, we're so close to a big breakthrough.
Yeah.
They think they are, but.
AI has been around for decades.
Yeah.
And some of the original AI, they try to do things like scene recognition. Can I take a video image, if I'm going to walk throughout this room and go around obstacles, I've got to be able to identify them, identify their boundaries and so on. So what kind of techniques would I have to be able to analyze essentially a 2-dimensional depiction of a 3-dimensional environment?
Yeah.
And figure out how to route my way through it. So I don't hold AI in the same regard, panic.
Yeah.
As a lot of other, we're a long way from.
Yeah.
Just look at some of the minor, albeit important anomalies they've had in these.
Yeah.
There's been recently several rather significant accidents.
Yeah, I think it was like one in Uber, they told them, don't test it, and they tested it, and of course it like ran the red light or something,
Oh,
almost
yeah.
hit somebody.
Yeah, so it, we're not there yet. Well, yeah, in fact, the thing on the scene recognition, that one serious accident where a guy was killed in Tesla. The car was next to one of these 18-wheelers, and the cargo box, or whatever they call it, was solid white. And it couldn't detect what the boundaries were, and crashed into it.
Yeah, it was all the same color.
That was all over the news for a while.
What?
I didn't even see that.
crash was all over the news for a
What car
while.
was it?
Yeah, that
Cars or something?
happened a couple months ago or something like that.
They didn't care about that one.
But then there's an example where it was something that was not accounted for.
Yeah.
And the AI was sophisticated
Oh, that's
enough
interesting.
to adapt
Did it
to
come?
unknown situations.
Damn.
Yeah. I think it's that adapting on the fly that's where there needs to be some kind of breakthrough, because
Oh, absolutely.
they've done all the learning and stuff, and they can make the big data set and learn on it, but it needs to be learning while it's doing
And
it
that's
as well.
like, for humans, you can adapt to situations.
Yeah.
And that's what differentiates us from computers.
Yeah.
Can you adapt to a situation that's not anticipated?
Yeah.
They definitely have like suicide.
So anyway, that's what the genetic algorithms class is on.
Is that just offered in the fall, or is there other,
Yeah, I teach that every other year.
every other?
In Japan, it's the opposite. If you commit suicide, they charge your family. If you committed suicide.
That's crazy.
Yeah, you'll get charged like something like $100,000 if one of your family members.
After the JTAG node
commits
has
suicide.
been identified by the FPGA, the JTAG pins become activated and the JTAG interface is used as a communication channel for the FPGA to be configured. This channel can also be used to create a boundary scan chain. The boundary scan logic is dedicated as part of each Xilinx FPGA and has all the mandatory elements to suit the IEEE standards. The JTAG mode allows the user to easily cascade any number of FPGAs into one chain for programming or debugging. JTAG mode allows a bitstream to be downloaded to each of the FPGAs in the chain with only a programming cable and a 4-pin JTAG header attached to a demo board. Since reconfiguring in this mode does not require any memory components to store the bitstream, this mode is primarily used for debugging and not for the end use of an application. This flow is possible because Xilinx FPGAs are SRAM-based and thus reprogrammable. This means that the user only has to generate a new bitstream with the impact utility and then re-download the new design into the FPGA. While Xilinx does not specify configuration times, downloading the JTAG takes between a few seconds and a couple of minutes. This is done default cable speed and the platform cable USB being used. Now this will vary depending on your PC, FPGA, and as I mentioned, the programming cable you choose. Impact is used for file generation and configuration of Xilinx's FPGAs. The impact utility is included with the ISC tools. It can also be used to program a CPLD or a Xilinx PROM and indirectly program a third-party flash component using the BPI or SPI configuration modes. Xilinx provides a number of programming cables that lend themselves to various purposes.
I'm going to
We'll talk more
discuss
about this
download cables
in
as well.
configuration 2. Just make sure after selecting a suitable cable, you have also planned for an appropriate cable connector to be available on your board. The impact utility programs FPGAs through several parallel cables, including the platform cable USB. In master serial configuration mode, the FPGA provides all the necessary control logic. In this case, since the control logic is fixed, this is one of the easiest configuration schemes to debug. All 3 mode pins, first of all, are tied low for master serial configuration mode. One of the things you might be wondering is, why master? Well, since the FPGA is providing the control logic and driving the necessary control signals, the FPGA is the master of the system. Unlike slave configuration modes where external control logic is required and the FPGA does not handle configuration of itself. The FPGA generates its own configuration clock in this mode. This clock is then driven outside the FPGA to a serial data source, usually a Xilinx platform flash. In response to the clock, the PROM provides the data 1 bit at a time. The configuration scheme is the slowest in this case of those offered, but is also the easiest to debug. This mode is used when data is stored in a serial PROM. Xilinx offers a variety of platform flash densities to accommodate the case where a designer has a multiple FPGA daisy chain and wants to store all the FPGA bit streams in one flash device. For more information about this, check your device's data sheet or the user configuration guide. Now this configuration scheme is the slowest configuration mode, again, but the easiest to debug since the control logic is fixed. In slave serial mode, an external host, such as a microprocessor or microcontroller, writes data serially into the FPGA. Since the clock and the control logic are built by the user outside of the FPGA, it is imperative that the user build the control logic to provide the serial data to the FPGA with sufficient setup time before each rising edge. If you're planning to program multiple FPGAs in a daisy chain, the data out pin will be connected to the data in pin of the next FPGA. The advantage is that the user could store the bit streams for multiple FPGAs in one external memory resource other than a flash PROM. And depending upon the...
Okay, so this one isn't that clear. This is the one where that control logic might be a microprocessor on the printed circuit board that is externally FPGA. So it's going to go out to its memory, get the configuration information, and then feed it a bit at a time to the FPGA. So there's a direct connection between the FPGA and the microprocessor. In effect, the FPGA is memory mapped to the microprocessor chip.
This may be beneficial as well as cost effective. Note that this configuration mode is rather slow, only loading data 1 bit per clock. Master select map, like the other master configuration schemes, has its control logic already included with the FPGA. The difference with this master configuration scheme is that it loads the configuration data 1 byte at a time, even though it is internally serialized. So this mode does not configure any faster than a serial configuration mode. Note that the Xilinx Platform Flash XL is often used for this configuration mode as the data source. The use of the Xilinx Platform Flash XL enables faster configuration times when targeting Vertex 5 and Vertex 6 FPGAs because it supports BPI or byte-wide peripheral interface modes. In slave select map mode, an external host such as a microprocessor or microcontroller will write byte-wide configuration data into the FPGA using a typical peripheral interface. In this mode, the external host starts the configuration process by toggling the program pin and then monitoring that the init pin goes high. This indicates the FPGA is ready to receive its first data. The host asserts the active low chip select signal, that's CSI_B, and the active low write signal, which is read_write_B. The host then continues supplying data and clock signals until either the FPGA's done pin goes high, indicating a successful configuration, or until the FPGA's init B pin goes low, indicating a configuration error. In this mode, data can be provided with 8-bit, 16-bit, or 32-bit data lines when using Vertex 5 or Vertex 6. Note that Spartan 6 only supports 8-bit and 16-bit data line configurations. This configuration mode supports the use of asynchronous peripherals that provide a write stroke, which can be used to have the FPGA generate the 8 clock pulses necessary. This mode also supports a synchronous peripheral interface, where the control logic provides the necessary 8 clock pulses per data byte. Note that the Xilinx Platform Flash XL device is often used as the byte-wide data source. In this example, and in that case, no external control logic would be required. This assures the reliability of the configuration scheme's design and reduces your risk of debug time. The serial peripheral.
Okay. The two configuration modes I will expect that you are familiar with are JTAG, and I will discuss JTAG after this video, and the SPI. SPI is extensively used in embedded applications. So JTAG and SPI are the two that I expect you to be familiar with.
Interface or SPI configuration mode is supported for Vertex 5, Vertex 6, Spartan 3E, and Spartan 6 FPGAs. This configuration mode allows the FPGA to configure itself from an industry standard SPI flash PROM without construction of your own control logic. The FPGA generates a clock signal and drives a command to the PROM. The PROM then responds with the appropriate data. This mode also supports multi-boot applications where additional bit streams can be loaded by the FPGA on command. This data is loaded serially and thus is not a fast configuration scheme. In Vertex FPGAs, the FPGA requires the vendor select signals, that is the VS, which is 3 bits wide. These bits are used by the PROM to determine which vendor's SPI flash PROM is being used and which commands to issue. However, if you're targeting Spartan 6, these signals are not needed since the first command code issued is always recognized. If you're planning on using Spartan 6, note that it also supports 2-bit and 4-bit data lines. The commands for SPI operations are vendor specific, therefore it is useful for you to make sure that you are using a supported SPI flash PROM. However, most devices will use the common commands supported. Check the device datasheet for a list of the currently supported PROMs. Currently, these vendors include Mnemonix, Spansion, Winbond, and Atmel. Users should plan on selecting a flash PROM that has sufficient size to contain the FPGA's entire bit stream. Refer to the configuration user guide for your device family. Find the size of the bit stream for your density of FPGA. You should also be aware that if your daisy chain contains multiple FPGAs in the configuration scheme, your flash PROM will need to be big enough to contain all the bit streams in the chain. Likewise, this is a popular configuration for designers that want to load a single FPGA with different bit streams at different times while their application is still running. This reconfiguration is referred to as multi-boot applications and should be planned sufficiently so you can choose a SPI flash PROM that is sufficiently large enough to accommodate all the additional necessary bit streams. If you're building an embedded application, it is also possible to store your software code in the flash PROM as well. So likewise, plan on choosing a sufficiently large enough PROM to store your software. Note that the available SPI flash proms use a single 3.3 volt supply voltage. All of the FPGA SPI flash interface signals are within specific I/O banks. Consequently, the supply voltage for the I/O bank must also be 3.3 volts to match the SPI flash prom. This implies that any I/O pins assigned by the user into the I/O bank must also be 3.3 volt compatible. Spartan 6 is 3.3 volt compatible, however, Virtex 6 is not. This means that if you are targeting Virtex 6, you'll need to build the external interface circuitry. For more information on building this interface circuitry, refer to the Xilinx Solutions database for more information. The majority of SPI flash prom vendors do not yet build a SPI flash prom that is compatible with Virtex 6, but check with your vendor for availability. In BPI mode, the FPGA configures from a standard parallel NOR flash prom. The BPI configuration interface is primarily designed to support standard parallel NOR flash proms. The interface supports both byte-wide, that is by 8, and byte-wide half-word, by 8 and by 16 proms. The BPI interface can work with other asynchronous memories that use a smaller SRAM-style interface, such as SRAM, NVRAM.
Give you a little bit more information on this later, but effectively in the BPI mode, you're just using a standard memory chip. And the FPGA has to provide the address along with any command and control signals. Notice the size of the address bus. It's 27 bits. That should give you an indication on how much configuration data is actually needed to program an FPGA. It's in the megabit region. But I'll give you some actual numbers later on.
EEPROM, or a mask ROM. As you can see, in these cases, no clock is needed because the FPGA contains the control logic. As an FYI, a NAND flash memory is a different technologies. FPGAs do not configure directly from NAND flash memories. Note that the flash device can also be used in embedded software applications where it may be necessary to store a system's software in a flash device, as well as the FPGA's bit stream. In an embedded application, such as one targeting the PowerPC or a MicroBlaze processor application, the platform flash can store the application code, then after configuring the FPGA can transfer the software from the platform flash to an off-chip memory, usually an SDRAM. The software code is then executed from that external SDRAM. FPGAs support two versions of BPI configuration. BPI up starts configuring the FPGA starting from flash address 0 and automatically increments the memory addresses. This is the most popular mode and most likely the primary mode to be supported in future FPGAs. The other version, called BPI down, starts configuring the FPGA from the highest memory location and automatically decrements the memory addresses. This addressing flexibility allows the FPGA to share the parallel flash prom with an external or embedded processor. Depending on the specific processor architecture, the processor will boot either from the top or bottom of the memory location. This allows the user to maximize the use of their flash device by allowing the software code to be stored in the same flash device as the bit stream. Note that BPI down is not supported for Spartan 6 devices. The BPI interface also functions with Xilinx parallel flash platform flash proms, which includes a 128 megabyte device. There are a number of supported NOR flash memories that are currently supported, including mnemonics and Spansion. But be sure that you check the configuration user guide for your FPGA's uncompressed bitstream size. This will help you determine which NOR flash prom is big enough for your bitstream and, if necessary, your design software code. Now let's wrap up this module with a summary. Field programmable gate arrays are usually configured on PowerUp from an external data source. SPI and BPI are the simplest configuration modes and take the least effort to debug. This is because all the configuration control logic is stored inside the FPGA or external memory device. Slave configuration modes take the most effort to debug because they require the user to build their own configuration control logic. JTAG access enables much easier testing and debugging of your prototype and while your system is in production. It is always a good idea to support a JTAG configuration scheme when building your system in case you need to debug your design later, for whatever reason. My first question, should my FPGA load its configuration data from an external memory resource, or should a...
We got the summary. Okay. So let's talk a little bit more about this JTAG. Okay, so JTAG was originally a consortium of companies that came together, and this ultimately became IEEE standard 1149.X. I'm not sure what it's up to now. And what it does is it defines the test access port and boundary scan architecture. It was not developed as a method of just programming FPGAs. It had a much broader application for it. It was actually developed to support testing of chips and printed circuit boards. It was one of those things that somebody said, hey, I can use that for FPGA programming. Just like Verilog was initially developed to describe digital designs. It wasn't until later that somebody said, gee, I can actually, since I have a description and I can simulate it, why don't I go the next step, synthesize and be able to program programmable logic devices. All right, so this is what the implication of JTAG is. This is a chip that supports JTAG. This is a general chip. And chips that support JTAG are referred to as being JTAG compliant. If you are JTAG compliant, you have to have, this internal logic could be anything. In our case, it's an FPGA. For each pin, you have to have something called a boundary scan register. And we'll take a look at the internal architecture of that shortly. Here are you have to add 4 additional pins to the chip. TDI, TMS, TDO, and T-clock, which are all JTAG pins. And you have to add some additional circuitry in there, a data register, an instruction register, a bypass register, and something called a TAP controller. TAP standing for Test Access Port. Test Access Port. So each input pin and output pin is going to have one of these boundary scan registers between the pin and the logic. And this is what it actually looks like. First, we'll take the broad view here. I wish they could do something to get rid of that reflection. So your boundary scan register is going to have a parallel in to parallel out, and then serial in, serial out. The parallel in, parallel out is the normal function of the chip. It's from the pin directly into the logic inside the integrated circuit. The shift in and shift out allow you to connect all of these boundary scan cells, as you see here, into one big shift register. TDI being the input to the shift register. Wrap around and come out through TDO. So, if I want to load these registers to use this thing in normal operation, unless for the sake of simplicity, assume these are inputs and these are outputs. I would use the parallel in to parallel out mode to use the chip in the normal operational method. Or what I could do is serially load the registers, apply the input, capture the response in these registers, and then shift everything out. So through TDO, I can get the response of this circuitry to this input. And when I'm shifting out this result, I can shift in the next input I want to apply. So I can kind of overlap those functions. This is a little more detail on what that boundary scan register actually looks like. You see the parallel in to parallel out is just a register. That's it. But you have some other registers in here which are used to update, to capture information, etc. Here's your serial in, and you go through to this register, and the Q output is the shift out that would go to the shift in of the next register. So here are the 4 pins associated with JTAG, and this was extracted from a application note on programming the Vertex FPGAs. Test data in, test data out, TMS, and test clock. And down here is a description of those, and I'm not going to read to you. This will be available in the lecture notes, and you can get more information on those 4 signals. Now this whole architecture is controlled by the TAP controller, Text Access Port Controller. And the Text Access Port Controller is actually a 16-state finite state machine. You'll see there are 2 columns here, and these are almost identical, except these have DRs and these have IRs. Select DR scan, select IR scan. Exit 1 DR, exit 1 IR. Pause DR, pause IR. And if you look at the arcs, they're almost identically located. DR stands for data register, IR stands for instruction register. You have 2 additional states, test logic reset and run test idle. Now, this test logic reset is your initial state in the finite state machine. All finite state machines, as you know, require an initial state. And normally, in a finite state machine implementation, you would have an external signal called reset or initialization that you would assert to force the finite state machine into the initial state. This uses a rather clever way of getting into that initial state. First of all, you notice on the state transitions, this is a more finite state machine. The the input to the finite state machine, I'll write this up above. TMS, test mode select, is one of the 4 pins for JTAG. That is what the input is. Now here's how they get this into the finite state, into this initial state, without requiring an external reset signal. You set test mode select equal to 1, and you clock it 5 times. And you're in the initial state. When I first powered this thing up, I could be in any state. Pick a state, initial state.
Shift DR.
Shift DR. So let's suppose the thing came up in Shift DR. I'll set test mode select equal to 1 and give it 5 clocks. 1, 2, 3, 4, 5, and I'm in test mode, in test logic reset. Let's suppose I came up in this one. 1, 2, 3, 4, 5. So that's all that's required to get it into the initial state. Now, I want to show you this, and we'll walk through a few of the states. Those 19 steps are required to program an FPGA using a JTAG interface. So let's take a look at these. On power up, place a 1 on the test mode select and clock 5 times. So TDIs don't care, test mode select is 1, clock 5 times. We just showed that. So that's going to put me in that state. Next thing you do, you want to move into the RTI state, and that says, don't care about test add in, I'll put a 0 on test mode select and give it a clock. Test mode select is 0, give it 1 clock, I'm in RTI. Move into the select IR state, put a 1 on test mode select and 2 clocks. 1, 2, I'm in select IR scan. Enter the shift IR state. A 0 on test mode select and 2 clocks. 1 clock, 2 clock, I'm in shift IR. Start loading the config in instruction. I need to put 0101 on test mode select and give it 4 clocks. I'm in shift R. Let's see, test mode select is a 0. So I'm going to stay in this state, but I'm going to clock 4 times, and test add in will clock in new depth. So you see how you can move through the finite state machine as you follow these instructions. Here's the key thing, is to go down to number 9, number 8. If I follow these steps, eventually I'm going to get into the shift DR state. That one. Test mode select is going to be 0. So on any succeeding clocks, I'm going to stay in that state. And notice what you're clocking in. The bits of the bit stream. So it's in this step 9 that you actually get to clocking in the configuration information. Then after you've got all the information in, then these are the cleanup steps, and you go through to 19, where you return to the RTI state when you're done. So these are the steps you would go through to actually program the FPGA through the JTAG interface. I'm gonna So I'm going to conclude with this statement right here. Impact is software provided by Xilinx that actually runs the JTAG. And as it says here, it uses a sequence of JTAG instructions to perform specific verification. And we just went through and saw those. These software tools do not support individual JTAG instructions. In other words, you can't write your own sequence of JTAG instructions to do something and expect to use the Impact software to do that. The JTAG driver software in Impact is designed for one and only one purpose, and that's to do those 19 steps to program an FPGA. Okay. So next time we will look at the JTAG download cables and see how those come into play. And then I'll talk about the BPI and SPI tools.